Hey guys, Professor Ackerman here. What I want to talk about today is how to do a transient heat transfer analysis using SolidWorks. And I'm going to use this example of a plastic filament extruder where you would put plastic pellets into some kind of hopper or receptacle, and then it gets turned by a screw to move through an extruder to make a certain filament diameter. So that'll be the example I'll be using here today. And there's a couple of things in this simple extruder model that I want to talk about. There's only 4 parts. We've got the tube, nozzle, filament, and the screw core itself. So let's open up the tube and take a look. So a couple of features here. This is just assumed to be a standard steel tube or pipe that I'm going to be using to build the body of the extruder. Note that you do need to specify the material for every element inside a heat transfer simulation. So if I take a look at plain carbon steel, for example, I can look at the material properties, and the thermal expansion and conductivity and specific heat are important for the kind of SolidWorks heat transfer simulation we're going to be doing today. So I'm going to assume it's plain carbon steel. There are other materials that are better. Perhaps aluminum or copper would have way better thermal conductivity. But this is a good starting point because steel is readily available in these kinds of pipe formats. So that seems good for now. A couple other features I added. One is a split line. So I added 2 split lines here and here. And the reason why I added those split lines is so I can locate where my heaters are going to be in this system, because I need a place to put heat into the system. And so I drew a rectangle, and then I went up to curves under the features tab, split line, and clicked on the outside of the pipe to create these split lines all the way around the pipe, which is where my heaters are going to be located cylindrically, as if I was using heating bands. I also did add this little divot right here. So it's just a little cut revolve that I made. And the point of that is to create a vertex where I'm going to be able to locate in the simulation for transient heat transfer where I want my system to control the temperature at. And that's going to simulate, in a real system, it would simulate something like a digital temperature sensor or a thermocouple at that location, which will be, in this case, I'm putting it near the nozzle. And that's going to be able to help us control the amount of heat going into the system. I did also add a cutout for the hopper over here, just so I can see, as heat flows through my system, what's going to end up happening at the entrance where I do have new plastic pellets coming in, and then they're being funneled through the screw into the heating zone and then out as filament. So those are the basic features I have for the tube. Let's go back and let's take a look at the nozzle. So I just assumed that this is going to be perhaps laid down from a steel stock rod. So I made it plain carbon steel. And I'm just going to assume for simplicity that this is butting up against the edge of the pipe. And we do have a 1.75 millimeter diameter hole in there. All right, so that is the nozzle. I do have the filament. Let's take a look at that. Okay, so this is what the filament looks like. We've got a solid hunk of plastic for now. Essentially, I'm just assuming that the screw on the inside is completely surrounded by solid plastic. Just as a simple approximation to get started, realistically, towards the hopper, you're going to have plastic pellets coming in that will have air in between them. And they're going to be individual pellets that are going to move through the screw system and start to melt. And then eventually, towards the nozzle, we will actually be basically we'll have fully melted plastic, and so it will look something like this with the parameters of plastic. I did also include the filament itself over here that I can put through the nozzle and then the first part out, just so I can see how the heat is going to be distributed through the end of this liquid plastic into the filament that's coming out of the extruder, so I can see what that heat distribution looks like as it's coming out and being cooled. I did add a small cavity here for the screw, and I defined this plastic as a polypropylene copolymer. If we go ahead and take a look at that, there are many different types of plastics we could identify and use here, but polypropylene is a pretty nice material to work with, relatively lower melting point than some plastics, and it extrudes pretty nicely. So I'm going to start with this. We can always adjust that later, or find a plastic that's at least similar to the material properties that we expect in our system. You can also define your own custom materials as well with parameters from other sources. So we're going to go with that, and so we got polypropylene copolymer. All right, and the last part is the screw core. And to keep it simple here, I just decided to model the screw that's going to funnel the plastic pellets through as a solid hunk of steel. So if you're using something like a drill bit or a typical extrusion screw, you might be using a steel because it's one of the most common materials used for drill bits and augers. And to keep it simple, although there are spiral flutes here, I decided not to model those so I can simplify my mesh. Anytime you're doing a simulation, it's always a good idea to make your simulation as simple as possible at first, just so you can get a result, and then from there you can refine your results as needed. So always start simple. So just representing the screw in this case as a rod. Okay, so I think we are good to go. We talked about the different parts that make up this assembly. Let's take a look at a section view here. So I created a plane right down the center, and this is what it looks like when it's assembled. We've got the tube on the outside with all that geometry mentioned. We have the steel rod in there representing the screw, and then I've got plastic, in this case, surrounding the steel rod, as well as going into filament at the end to a 1.75 millimeter diameter, which would be used for something like 3D printing. Okay, so it's looking pretty good. Now I think we're ready. We have our assembly. Let's go ahead and create our heat transfer simulation. So what I'm going to do here is go right click on the study. I did already define one earlier. I'm going to create one from scratch just to show you what's involved here. So we're going to go to new simulation study. I'm going to go down here to thermal analysis and click check. Okay, so we just started our thermal study. Now, one thing about the thermal study, let me remove my section clipping for a second, is the default is always going to be a steady state simulation. Let's open up the properties of the thermal study by right clicking it, go into properties, and we see that it is defaulting to steady state. Now what that means is if I did run this simulation, it would assume that after some amount of time, it's going to balance the energy in to the energy out in your system, and then it's going to tell you what the steady state temperatures would be after a long period of time, and or even a short period of time, basically some amount of time. But what I'm really interested in for this analysis in particular is I want to know how long it's going to take from a room temperature. I want to know how long it will take to heat up the plastic inside the extruder. It's essentially a cold start, right? Now, once everything is up to temperature, the plastic will melt much more quickly because the steel outer tube as well as the screw itself will all be hot. But I want to know how long it's going to take in the worst case if I start from room temperature to start heating from there. So to do that, steady state won't necessarily tell me the amount of time it's going to be required to heat up our system. It'll just tell me based on the energy in and energy out what the steady state distribution of temperatures will look like. So for this application, I'm going to switch it over to transient. Click on that. And now we have a couple different options. So for the total time, I don't know how long it's going to take to heat up this plastic. If I had to guess, somewhere from, 5-10 minutes maybe, roughly, depending on the amount of power that we put in. So it could be 10 minutes, it could be 20 minutes, it could be anything. Let's start simple. Let's assume it's about 10 minutes. So I'm going to go with a total time of 60 times 10, 600 seconds to be 10 minutes. And then I also need to get the time increment down. So I don't need a very fine time increment here. It's not going to have a big effect on the stability or results of the model. So what I'm going to choose is a pretty large time step just so I can get the simulation going quickly and take a look at the results. I'm going to choose 30 seconds for my time step. I could always go back and refine that later to get more accuracy if needed. I'm going to leave all the defaults here. I'm not really going to look, I'm going to define my own initial temperatures. I don't really need to consider fluid convection effects in this example. And I'm just going to see how this goes initially. Okay, so total time 10 minutes, time increments 30 seconds. Awesome, so that's our transient study set up. Now when you're doing a transient study, you do need to define initial conditions for temperatures. So because we're going to assume it's a cold start starting at room temperature, I'm going to click on temperature. I'm going to change this to initial temperature. This option is only available for transient studies. And then for our initial temperature, I'm going to just select the entire part of each part in the system. So I'm just clicking on all the parts, and I'm going to assume that everything is starting in the worst case at room temperature, which we can just say, let's say it's about 25 C. Okay, so that's looking good. Define our initial temperature. All right, so now I need to define what my thermal loads are going to be beyond the initial condition of the temperature. So I have a couple options here. We've got convection, heat flux, heat power, radiation. Heat transfer can be kind of complicated. All these effects can matter. But to keep it simple, one option that we could consider is just defining a temperature at these heater bands, right? I could say hypothetically these heater bands will maintain exactly, say, 300 degrees Celsius to melt the polypropylene at around 200 Celsius roughly. And then if I set these as a constant temperature, I could see how long it's going to take for the heat to move and distribute throughout the system and look at the temperature distribution. However, no heater is exactly perfectly accurate, right? So that could be a challenge because the heaters tend to run a little bit hot to get the rest of the system up to the temperature based on your temperature feedback. So I'm going to go for a slightly more realistic simulation here that's particular to this application, where I want to go to thermal loads. I'm going to go to heat power, and I'm going to define where the heat is going into our system. So I'm going to assume they're going in through heating bands cylindrically around this extruder tube. I'm going to click on those faces where I have the split lines, and that's where my heater is going to be. So this is going to be per item. I'm going to stick with SI units. Let's say that I'm going to dump 250 watts of power on each one of these heating bands. Now, I don't know how much I need, right? That could come from other calculations or from this simulation. But let's just say I can find heating bands, for example, that can run 250 watts each. And those are readily available, they're inexpensive, I could apply them in my system. Let's just see what that would look like. I can always go back and refine this. The higher the wattage, the faster it's going to heat up. Because that's energy over time. And the lower the wattage, the longer it's going to take, but perhaps the less expensive it might be as a final system. So let's just assume 250 for now, and if we need to, we can refine that later. Now, if I just assign 250 watts into these heating bands, what could happen is these could get very, very, very hot because this is just energy in constantly. And the steel tube can take up a lot of heat. And so the temperature of this can reach to very, very high temperatures. So if I just turn this thing on, the temperatures could get very large. And you can actually simulate that and then see what happens by just clicking check and running your simulation. But since I know that that's going to happen, I do know that I probably need to have some kind of controller in our system. And that's where that little divot I created earlier comes in. I'm going to go to thermostat down here. And this thermostat is only available for a transient simulation. I'm going to go click down here, zoom in on my divot that I created, and you need a vertex. So it has to be a single point inside the mesh where you can check the temperature, and the simulation can essentially turn on or off the heat power in based on temperature cutoff details shown down here. So I selected where it's going to go. So my thermocouple is going to go right there. And for the cutoff, I'm going to say I'm targeting, let's say I want to get up to 210 Celsius as a target. So I could say 205C is my lower bound here. My upper bound could be 215. So we can get right around 210. I could even tighten that up a little bit too if I wanted, 205 and 210. We could play with those parameters and see what happens. But essentially I want the heaters to heat up until this condition is met, and then try to maintain the temperature at that thermostat position or at that thermocouple position within this range. So the simulation should be able to automatically do that. So let's click check. So I've got my heat power set up, I've got my thermostat, or in this case a thermocouple at that location set up. So I should be good to go to start meshing the system and getting some results. All right, so the next step would be going to mesh. So I can mesh and run, but I want to see what the mesh looks like and make sure it's reasonable. I'm going to keep a default mesh just to make the simulation go faster. I can refine it for more accuracy later if needed. So let's see if that mesh, the default mesh, will work well. The geometry here is not particularly complex, so the meshing went smoothly. And let's take a look at the thermostat position, the thermostat. It looks like it has a pretty decent mesh with enough mesh triangles down there to represent the temperature at that location. So overall, it seems like that's a pretty good starting point. Okay, let's go ahead and mesh and run, and let's see what we get for our thermal study. So it's processing each step. Note that there are 20 steps because I have a 30-second time step, and I'm going to run my simulation for 600 seconds. So that will lead to 20 steps. And that's why I like to do kind of a coarse time step initially, just so I can get a result and make sure there aren't any major issues in my simulation. All right, looks like we're just about done. The thermal solver just completed the results. Okay, so we got some cool rainbow plots going on here. That's good. Now, first of all, I do have a temperature result, temp in Kelvin. What I like to do here is I don't use Kelvin as much, in daily life, so I like to edit the definition of that chart. I'm going to change it from Kelvin to Celsius. Click check, and now we see the temperature in Celsius. Now, note down here it says plot step 20, so this would be the final time step in this simulation. If I want to see what the first time step looked like, just go back one, and we can see right here the heating bands are immediately starting to heat up in the first time step because I'm dumping 250 watts in each of these locations. And I can continue to advance the time step, and I can see how that heat starts to flow. And it's pretty hot there initially, and then that heat continues to flow, and then it continues to adjust as well. Let's further visualize this by right-clicking on the thermal study, and we can go to animate. Now first though, what I would like to do is, let's go to the final time step. Before we animate it, I want to actually look inside the tube. So that's where we go to like a section clipping. I can define the plane I want to do the section clipping at that I define, that goes right down the center, and click check. And now I can see the results inside the extruder because it's symmetric. This is a pretty good representation, and I can actually see how those temperatures change over time. Let's see, there we go. I can see how they change over time inside of the tube. So now that we can see inside of it, let's animate it. It's going to take a minute to create the animation. All right, and this is going pretty quick. Let's slow it down a little bit just so we can zoom in here. Okay, so we can see the time steps. So here we go, time step 1 gets hot, heat starts to spread, the thermostat turns off the heater so that we can get a little bit more even heating throughout the system and allow it to spread. And it's looking pretty good. Okay, so our simulation seems pretty reasonable. Now let's go a little bit and dive into the data here. Let's figure out how long it took to get up to a reasonable temperature to melt the polypropylene. So what I'm going to do is right-click on the thermal study. We're going to go to probe. Since I have the actual section view here, I'm going to probe areas of interest to me. So I'm going to go perpendicular. I'm going to probe right here at the exit of the nozzle. I'm going to probe at the entrance of the nozzle. I'm going to probe right below that thermostat just so we can see what it's doing at that point. And I'm going to probe right below the heating band as well so we can see what's happening locally on the outside of that tube. And we could add more points if we want, but this will give us a good starting point to look at what's happening thermally in all these different time steps. Okay, so I've got the probes. I can move in time and check the temperature at each location during the simulation. But what I like to do is go down here to response plot, and that's actually going to show me the results over time of this simulation. Let's expand this. Okay, let's get that back. All right, so I've got the locations over here, so we can see that. And then let's take a look at our results. So this black line, these black data points correspond to location 4, which is the heating band. So we see that the heating band gets really quite hot initially. It goes over 500 C. Maybe that's a little bit too much overshoot in terms of our controller not being quite as responsive, because that's quite hot. This is a very simple control scheme, but it does get really, really hot. That temperature is moving through the steel pipe, and we can see at location 3, which is where our thermostat is located, the temperature keeps going up, up and up and up, and then right about here, it passes by, right in this time step, it passes by our thermostat lower bound. Then it turns off the heater band, and then it will turn that heater band off so that the temperature can come down, and it will try to maintain that temperature at that thermostat location, which is where you can see this really start to level off. Now there is a lot of overshoot here, so it's not a perfect control system, but it gives you a pretty good idea of what a real system might look like if you actually implemented a heater with a control system in this application. I could also refine this time step much more, and I'd get better control because I would have more data points in between these time steps. But this is a good start. Let's take a look at what's happening at the actual output of the filament. I need to be melting this polypropylene in order to make a filament of a reasonable diameter. And it looks like the location right here at the start and end of the nozzle are really quite similar. The blue and the red lines indicate that they match very closely, and they approach the thermostat temperature right up there. So heat's flowing pretty smoothly in the system, and that's looking pretty good. Now we could do a further refinement of these results and adjust some different parameters, different time steps, make geometry adjustments to get a more accurate representation. But that's a pretty good start. So let's answer our original question here. How long did it take to get to the, let's say we're targeting 210, right? So if I mouse over this data point right here, if I look on the very bottom of the chart right down here, I can see that it gets to 210 in about 213 seconds. And then it goes a little bit above that as well, which again, we'd have to refine that. So just to make sure, let's check what that's going to be so I don't have to do that in my head. 213 seconds over 60 seconds. So really just under 3.5 minutes in order to get the plastic from room temperature up to the temperature for a successful melting of the polypropylene to make filament. Now you can imagine if we started at a higher temperature, so if this was already heated up and warmed up, this time would go down drastically. And so that would be more of our steady state solution where we're just melting new polypropylene coming into the system and continually extruding the molten or liquid polypropylene that's gathering here towards the end, towards the start of the nozzle. So that's looking pretty good. We could save this information to Excel and do some more data analysis, or just save it for later. But this is a pretty good start. We answered our original question. We created a pretty reasonable simulation to get us started. And then from here, we could refine our results and get a little bit more accuracy. But that's a good start. One other thing I want to mention real quick that I think is interesting. If we go out of the probe menu and back up the plot to the final time step in this example. One thing that is kind of cool, because I'm heating over here, most of the heat is traveling towards this nozzle and really accumulating heat inside the nozzle before it extrudes the plastic out. I'm not really seeing a very high temperature at the input, which is actually kind of good because here we have new plastic pellets coming in that are solid, and we don't really want it to melt here because we want it to be moving through our system, through our screw, get to the heating zone, and then melts and become filaments. So that's kind of a good thing that the simulation shows us as well. And also the temperature distribution down here in terms of how the filament is proceeding, it gets really hot right at the end of the nozzle, and then it really starts to cool down pretty quickly. Now what we could do is add in, say, a convective heat transfer at the outside here, and we could simulate what would happen in a real extrusion machine, which is you need to cool the filament off. And so we could see what effect that has in terms of the results of the simulation. Because having some cooling here would definitely cool the filament down much faster, and it would become solid more quickly. So yeah, it's looking pretty good though overall. We got a pretty good simulation and a good framework where we could work with and then continue to refine our simulation to get any metrics of interest to us before we go ahead and spec out components and prototype and then actually test the real system. So I hope that was helpful. Hopefully this gave you a good foundation of how to do a SolidWorks transient heat transfer simulation with a real world example. And let us know if you have any questions. So hope it was helpful. Have a good one, guys.